Hi everyone, welcome to our weekly seminar series. It's my pleasure to introduce today's speaker and new member of our ENST family, Dr. Isis Scott. She has a bachelor's degree in agricultural engineering from Brazil. Then she moved to Purdue, where she did a master's degree in agronomy. And last December, she finished a PhD degree in agriculture and biological engineering. So we are very pleased to have her in our group. She is co-advised by Greg McCarty from USDA ARS and Dean Hively from USGS, and she's looking at sort of nutrient remediation using some of the new crops such as miscanthus to remediate nutrient pollution. So she's already off to a great start. I think this is her second month and she's already planning to do some field research very soon. Some other fun facts that you may not know about Isis is when she was doing a bachelor's degree, she came to Purdue to do an internship, and then she ended up spending several years in Purdue. Another fun fact about Isis is she was an English teacher, and I promise you, I'm not making it up, at the Wizard School of Languages in Brazil. Today she's going to talk about some of the work that she did in Midwest, looking at dissolved phosphorus losses in surface runoff. And as you know, phosphorus is our favorite nutrient in Maryland and Chesapeake Bay. So we're very fortunate and glad that she's here working with us. Thanks, Isis.
Thank you, Dr. Tour, for this introduction. Hello, everyone. Thank you all for being here today. I'm Isis. That's how you pronounce my name. So yeah, I just started here in Maryland this January, but today I'm gonna present a part of my PhD research. In this presentation, I named it the use and behavior of sorption media in mitigating excessive dissolved phosphorus in surface waters. So I'm going to start with a brief overview of our motivation and the rationale for this research, as well as a little bit on the state of science on excessive dissolved phosphorus and phosphorus removal structures. So we know that excessive dissolved phosphorus is a threat to water quality because it was one of the key drivers to cultural eutrophication and to harmful algae blooms, such as this one that I'm showing you here in this picture. So this is a harmful algal bloom in Lake Erie, which is our eutrophication landmark in the Midwest. It is showing a picture on August of 2019 when 620 square miles of the lake were covered with cyanobacteria. And this is not only a threat to water quality, but is also a threat to the aquatic ecosystems, to drinking water supply, to the local economy and recreation activities. The bad news is that the intensity and the frequency of these blooms are expected to increase during the 21st century. And with that, what that means is that we need more effective and more new phosphorus pollution mitigation practices to overcome issues such as this one shown in the picture. We know that in many watersheds, agriculture is the main source of phosphorus. And we also know that traditional mitigation practices of non-point phosphorus pollution have been somewhat insufficient to sustain low phosphorus levels in water systems. And one of the reasons for that is because those traditional mitigation practices, they are much more focused on particulate phosphorus. And this is the phosphorus pool that is transported with sediments. And it's easier to prevent. These BMPs or best management practices are effective. And on the other hand, we have the dissolved phosphorus. And this is the phosphorus pool that moves with runoff, with subsurface drainage. These traditional BMPs are not as effective. And the concern with this phosphorus pool is that it is 100% bioavailable for aquatic biota, meaning that as soon as it reaches a water body, it will start immediately causing problems such as that one that we saw in the picture. So in essence, what I'm saying here is that dissolved phosphorus is a more potent eutrophication agent. And because of that, we need more targeted mitigation practices that deals specifically with the dissolved phosphorus pollution. And that's exactly where phosphorus removal structures come in. So these structures, they are landscape scale filters containing phosphorus sorption materials, which I'll be calling them PSM throughout this presentation, that have a chemical affinity for dissolved phosphorus. So the way that they work is that they will receive a high phosphorus flow. It can be from a subsurface flow or surface flow. And that high phosphorus is normally greater than 0.2 milligrams per liter. And then that flow will then be treated by the PSM inside the structure. It will flow through the PSM, and then we will end up with a phosphorus-free or almost phosphorus-free water. This is how these structures look like in real life. So here I'm showing you two examples of phosphorus removal structures. These are the most recent ones that we built in Ohio and in Indiana. And in here, I just wanted to show you how the installation of these structures look like. These are just the most recent ones. The phosphorus removal structures, they are extremely flexible for different landscapes, for different environments, both urban and rural, and we can adapt the design of these structures according to the needs. But essentially what we have is a set of pipes on the bottom, then we come up with the PSM, and then another set of pipes will connect this structure to the tile drainage, and the bottom set of pipes will connect that structure to the closest ditch. And the core of these structures is phosphorus sorption materials, or the PSMs. They can be natural materials, which are, for example, iron oxides. They are normally minerals. They can be synthetic filtration products, which are those products that are produced and manufactured specifically for contaminant removal. And in this case, these materials are extremely efficient, but at the same time, they are extremely expensive. Or they can be industrial byproducts, and these are our favorites. They have the disadvantage of being regionally constrained, but they are extremely cheap. These different PSMs will have different removal mechanisms, and because of that, they will also have different efficacy on phosphorus sorption. The dominant mechanism for phosphorus removal will depend on the main or dominant component of the PSM. So we can categorize these PSMs into two main categories here. So the first one being calcium and magnesium-rich PSMs. And in equation one, I'm showing you how the removal mechanism will look like for these type of PSMs. It is a calcium precipitation reaction. And we also have aluminum and iron-rich PSMs, and the removal mechanism would be dominantly a adsorption reaction or a ligand exchange reaction. And this differentiation is important because we will have different impacts of time, different impacts of pH, and different possibility of reversibility of the reaction. At the end, we want to find a PSM and a removal mechanism that will work better for any specific design for a phosphorus removal structure. And knowing these, the removal mechanisms and what is behind it, we can find what are the optimal conditions for them to happen. So with that in mind, we designed this PhD research, which was named The Use and Behavior of Phosphorus Sorption Materials. In this presentation today, I divided my topics in three main portions. So the first one being, I'm going to talk a little bit about steel slag characterization. So this is our first work in which we tried to relate the chemical and physical properties of steel slag to their ability to remove phosphorus in phosphorus removal structures. The second piece of research that I will be presenting today is about the PSM regeneration and phosphorus recovery. So essentially in this work, we tried to establish a standard regeneration technique that was able to improve the longevity of PSMs by treating them when they are saturated with phosphorus. And the third research topic that I will be presenting today is the behavior of iron-rich PSMs in anoxic environments. And the idea behind this topic is because we wanted to be able to build structures with a bottom-up flow, which means that we would have stagnant water in the structure. So we wanted to know how the iron-rich PSMs would behave under those conditions. So now I'm going to talk a little bit more in detail about each of these researches, starting with estimating the variability of steel slag properties and their influence in phosphorus removal ability. First, what is steel slag? So steel slags are a byproduct of the steel industry. In the US, they are typically used as aggregate in civil engineering applications, including road construction, and its excess is normally sent to landfill. In recent years, there has been an increasing interest in using steel slag for water and wastewater treatment due to its low cost and wide availability. Specifically for phosphorus, we are interested in steel slag because of the predominance of calcium minerals in its composition. And in this picture here, I'm showing you how different steel slag samples look like. So the ability of steel slag to remove phosphorus is well documented in the literature, but it is highly variable. So in a literature review by Penn and co-authors, it was reported that the cumulative phosphorus removal by steel slag varied from minus 150%, meaning that actually steel slag was contributing phosphorus to the flow, to 89%. And the potential causes or sources of variation can be divided in two main categories. So the first one being extrinsic factors, which include phosphorus source, for example, which can be from wastewater or from tile drainage, phosphorus concentrations, since we know that some of these removal mechanisms are concentration driven, residence time, and which is the contact time between contact time between the PSM and the incoming flow, and the type of structure. In the intrinsic factors include the origin of the material, the source of the raw material that was used to produce the steel slag, the steel making processes, and all of these reflect on a different chemical and physical nature of the media that is produced. So with that in mind, we established our main question for this research, which is phosphorus removal capacity of steel slag impacted by its inherent chemical and physical properties, source and production processes? And spoiler alert, the answer to this question is yes. And since we were able to find poorer slags in terms of phosphorus sorption capacity, we then asked, can we improve the phosphorus removal ability of those slags that didn't perform very well? And in order to do that, we proposed two different techniques. The first one by aluminum coating the steel slag. And for that, we used solutions of aluminum sulfate solutions with different strengths. And the idea here was to add a different mechanism path to the calcium precipitation reaction. So we would have both calcium precipitation as well as a aluminum adsorption reaction. That was our expectation. As well as we also tested allowing longer residence times for steel slag to operate, since we know that the calcium precipitation reaction is dependent on time. And at the end of this research, we also asked, can we predict the phosphorus removal ability of new steel slag samples, of those slag samples that we don't know how they will perform, but we want to be able to select the best ones. So that was our motivation in here. In order to study that, we selected 18 different seals slag samples, and these are the parameters that we initially tested. So they are from different production plants, they are produced through different steel-making processes, and they are of different sizes. We conducted the characterization on uncoated, 70% coated, and 100% coated steel slag samples. And in this table here, I'm listing to you all the parameters that we evaluated. I won't go in details about the methodology that we used, but I would like to talk to you a little bit more about how we estimated the phosphorus removal capacity of these materials. So we developed a flow-through setup in which we had a constant inflow of phosphorus from a Marriott bottle. In this research, we are using 0.5 milligrams per liter of phosphorus. And this inflow would be in contact with the PSM that is inside here in this flow-through cell for a certain amount of time that we pre-established based on the flow rate. And then at the end, we would select several samples at predetermined sampling interval. At the end of each of these experiments, we had a graph that looked like this one on your right. So in here, I'm showing you two replicates, which represents two different experiments, and each of the dots are one sample is one sample that was collected during the experiments. In the graph here, I'm showing you the cumulative phosphorus removal in percentage in the y-axis, and the cumulative phosphorus added in the x-axis. And what is important here in this graph that I would like you to notice is this vertical line in here. The intersection between this vertical line and each of the curves is the measurement that we used to evaluate and to compare the different ability of steel slags to remove phosphorus. And that is the cumulative phosphorus removal in percentage after we added 60 milligrams of phosphorus per kilogram of PSM. And we can talk more about why I chose 60, but that's what this vertical line is representing in here. So when we put all those measurements together, this is what this is what it looks like. So we have the cumulative removal varying from -55 to 100%. And in this graph here, we can already see a potential source of the variability. So in here, I'm showing you in the gray dots, the uncoated samples, and you can see that its distribution is much more random in comparison to, for example, the 100% coated slags, which are much more concentrated on the top graph here. Okay, and then we started to analyze what are the potential causes for this variability, right? The extrinsic causes of variability that we evaluated included residence time and the level of coating. Our findings are summarized in here, and essentially what we saw was that for uncoated steel slags, those slags performed better under the higher residence times. And we saw that 9.85 minutes was already sufficient for steel slags to perform, for uncoated steel slags to perform at their prime. For coated steel slags, we saw that it can perform under lower residence times, such as 0.28 minutes. And an unexpected impact of the aluminum coated was that we ended up with a more uniform media. Which means that, so if we have lots of different uncoated steel slags versus lots of different coated steel slags, we would be more confident in predicting the ability of the coated steel slags on removing phosphorus in comparison to the uncoated steel slags. And at the end, we concluded that the 100% aluminum coated steel slags should be used in those structures that are for which that expect a higher flow rate. And then we also analyzed some of the intrinsic causes of variability, starting with the production processes. So we saw that the blend production processes was significantly inferior in comparison to the other 4 production processes. And we attributed that to the fact that the material had a lower porosity as well as a lower buffer intensity. But still, production process was not able to explain everything, to explain all the causes of all the variability of the phosphorus removal capacity. So we went to find what are other causes or other causes of variability. And that's when we analyze the chemical and physical properties of steel slags. So you see these models in here, and they are, we use these models to predict the ability of steel slag to remove phosphorus. And the first model that I'm showing you in here, the first equation is for uncoated slags. It was able to explain 70% of the variability of steel slag in removing phosphorus, while the second one for coated slags was able to explain around 55 of the variability of steel slag to remove phosphorus. In practice, this means that we can use these models to make a preliminary assessment of how a steel slag will perform in a phosphorus removal structure situation based on these characteristics that I'm showing you in here. Okay, so now I go back to that first slide in which I presented you the questions, and now I have some answers. So the phosphorus removal capacity was impacted by steel slag inherent chemical and physical properties. And we could see that for the poorer slags, we were able to find 2 different techniques that could improve their phosphorus removal ability. So aluminum coated slags showed a better performance under low residence times. And also by allowing longer residence times for steel slags to operate, we were able to have a better phosphorus removal. And that residence time is not like the wastewater treatment plant's residence time. It's just a 10-minute retention time, which is feasible in a field condition. And we also saw that we could predict phosphorus removability of steel slag samples, of new and unknown steel slag samples, based on the models that I just showed you. And also by analyzing the leached samples, as well as digesting the samples, the slag samples, we did not identify any environmental risks in the use of them, in the use of steel slags in an environmental setting. Okay, so at this point, we examined and we investigated one calcium-based PSM. We know everything that there is to know about those steel slags. And we also know that we can predict with a certainty its behavior in a phosphorus removal structure. But now we had a question about aluminum-rich and iron-rich phosphorus sorption materials. How can we improve their use in phosphorus removal structures? And the idea here was to establish a treatment procedure that was able to restore the adsorption sites on PSMs that were already saturated with phosphorus. So the question of this work was, can aluminum and iron-rich PSMs be regenerated instead of being replaced? And the reason why this is possible to do with aluminum and iron-rich PSMs is because of the removal mechanism. So in this equation here on the bottom, you see the sorption reaction on the forward direction. And with our regeneration methodology, what we were trying to do was to add a hydroxide anions to the solution, and with that force the equilibrium backwards. And we could recover the phosphate later, and we could also restore the adsorption sites on the surface of the PSMs. So in order to test these hypotheses and these regeneration methodologies, we used 3 different PSMs, Alcan and Biomax. They are both iron and aluminum-rich PSMs. They are commercialized as media for contaminant removal, and they are manufactured PSMs. And we also have phosphorus. This is an iron and calcium-rich PSM, and it is a natural material, also commercialized for contaminant removal. So our experiment plan involved the use of adsorption and desorption cycles, or phases, as we called it. And they would be sequential in our flow-through system. So first, we would start with an adsorption phase, and that we would use different phosphorus loading levels. So we used 0.5 milligrams per liter, and which is a representative of our upper bound of what we would normally find in tile drainage. And we also used 50 milligrams per liter, which is what we would normally see in kind of a wastewater range of concentration. And following the adsorption phase, we would then immediately make a desorption phase in which we use 1 molar of potassium hydroxide solution. So for the desorption phases, we tested different number of pore volumes of the regenerative solution being added. We tested different residence time, the contact time between the regenerative solution and the PSM. And we also tested different numbers of recirculations. And this is how the adsorption phase of Alcan and Biomax look like. This is the first adsorption phase for them. They showed very good efficacy, satisfactory efficacy in the adsorption phase in both levels. So in the first row here, I'm showing you their ability to remove phosphorus in the low loading level, 0.5 ppm. And in the bottom row, I'm showing you the high level of phosphorus. They were able to remove phosphorus at a good rate, and it's a material that we would consider for being implemented in a phosphorus removal structure. And the good news is that their regeneration was equally successful. So the way that we chose to evaluate the regeneration success was through this measurement here, which we called phosphorus recovery in percentage. It's essentially the relationship between the phosphorus that is desorbed and the phosphorus that was just sorbed in the phase immediately before. Overall, we saw an average phosphorus recovery for Alcan and Biomax of 81% and 79% respectively. And then for phosphorus, the regeneration treatment was virtually ineffective. And we attributed that to the fact that because phosphorus had a high concentration of calcium in it, and its pH is much higher than the Alcan and Biomax, we speculated that it was actually removing phosphorus through calcium precipitation rather than its dominant mechanism was calcium precipitation rather than ligand exchange reactions. We were able to find the most effective treatments, which were the ones that used 20 pore volumes of the regenerative solution and a residence time of 10 minutes without recirculation, or the one that used 5 pore volumes, residence time of 0.5 minutes with recirculation. And this is important because 5 pore volumes is a much more feasible volume to work with in the structures, in phosphorus removal structures. You saw the size of those structures. We normally use around 40 tons of the PSM. So it's a much more feasible, field feasible regeneration treatment. Okay, so in summary, this is what we found for this research. The regeneration technique that we developed was successful. So by using 1 molar of potassium hydroxide, we were able to treat and regenerate different PSMs and different levels of, at different levels of phosphorus saturation. The regeneration strategy can be repeated. So once the PSM is saturated again after one cycle of regeneration, we can regenerate it again, but with decreasing efficacy. And the regeneration is viable at the field scale with the volumes that we tested, which means in practical terms that the treatment that we developed is able to improve the longevity of PSMs in phosphorus removal structures. So, okay, so now we know a little bit more about aluminum and iron-based PSMs. But we still had one question regarding the behavior, the use and behavior of iron-based PSMs in anoxic environments. And as I mentioned in the introduction, the idea for this research is because we wanted to be able to build structures with a bottom-up flow. Normally, phosphorus removal structures are built with a downward flow, which means that it has free drainage and gravitational flow. But the problem with this design, in the flow regime, is that we have phosphorus removal structures that have a large footprint because we can't go as deep because we are limited to the water level of the receiving water body. On the other hand, if we use upward flow, we are not limited to the water level at the receiving water body. We can build deeper structures that have a smaller footprint in the field. The limitation with this type of flow regime is that we will have stagnant water in between flow events. With that, anoxic conditions can be developed in the structure, and then there can have changes can happen in terms of iron-bound phosphorus solubility because of the reductive dissolution of iron 3, changes in the iron-rich PSM chemistry. So how would that reflect in terms of their phosphorus sorption capacity? And we were also concerned about possible redox-induced changes in solution. Since these are all byproducts, or since we use byproducts in this research, we were also concerned about their environmental safety. Okay, so specifically for iron, under anoxic conditions, iron is reduced as it is used as an electron acceptor. We know that both iron 3+ as well as the iron 2+, they can react with phosphate through different mechanisms. So we hypothesized that despite of the reductive dissolution of iron 3, we would not have much loss of phosphorus because the iron 2+ reaction with phosphate would offset part of that loss. But still, we had contrasting accounts in the literature regarding anoxic conditions, so and phosphorus release. So in soils, we saw that in the literature, there are reports of anoxic conditions being associated with phosphorus release. In the wastewater literature, we saw that iron 2+ salts addition was actually resulted in a superior phosphorus removal in comparison to iron 3 salts addition. And regarding phosphorus filter media literature, we saw reports that said that phosphorus was released under reducing conditions as long as there was also low pH. These are the PSMs that we chose to test in this research. The first one is alkane. So we were really interested in alkane, so we tested it again in this piece of research. AMDR, or acid mine drainage residual, and metal shavings. We characterized these materials chemically, and we also analyzed their phosphorus removal ability in the same flow-through experiments that I showed you before. And it was important to have this evaluation because we then could saturate the PSMs to a certain level of phosphorus saturation and incubate both phosphorus treated or phosphorus saturated and non-treated PSMs. So we saturated the materials to a 60% level of saturation. And this is how our incubator looks like. So we have a constant gas inflow. There is regulated through a gas valve and a pressure valve, and then the gas then goes into a water bottle and goes into a manifold that will distribute the gas to our incubation vessels. The incubation vessels look like the picture here in the inset. And they are essentially they are essentially 250 ml centrifuge bottles that we had inserts on its lid for EH and pH meters. So with that, we had pH and EH measurements every 5 seconds throughout our incubation period. This is how it looks like in real life. So our experiment plan, in our experiment plan, we incubated non-treated PSMs and treated PSMs, and the composition of both of these samples is similar. So we had PSM, and then we collected tire drainage from a cornfield, and we also added a 5% solution of glucose. And with that, our intention was to provide the best conditions possible for microorganisms operating at their prime. But we also had some samples that we called reference samples, which is just the PSM and tire drainage, which is more representative of what we would normally have in a phosphorus removal structure. And we also had control, which is just the tire drainage. So these samples and its replicates were incubated until they reached a minus 200 millivolt as the incubation target for the EH. We chose this number because it is under the lower bound of iron reduction. And in the post-incubation analysis, we analyzed the solutions for iron 2 and iron 3 concentrations, as well as the chemical composition of those solutions. And for the non-treated PSMs, we performed new flow-through experiments because we wanted to see what were the effects of the anoxic conditions on the flow-through, on the phosphorus removal capacity of the PSMs. So all samples developed anoxic conditions once the incubation started, but the time to reach the incubation target of minus 200 varied between 96 and 600 hours. And I thought it was interesting that one control sample and 5 reference replicates out of 12 reference replicates did not reach the EH of minus 200 millivolts. These were the only ones that did not reach, and all of them didn't have sugar in it. Through the chemical characterization, we saw that alkane and AMDR had aluminum and calcium contents in addition to iron, which could also offset the effects of the reductive dissolution of iron 3 on phosphorus release. And we also saw that the metal shavings and AMDR contained the higher total and oxalate extractable iron. From the literature, we know that a higher concentration of oxalate extractable iron normally is related to a higher concentration of dissolved phosphorus in solution under anoxic conditions. So this is how the data from the incubation looks like. So in the top graph here, I'm showing you the pH data across all the elapsed hours for 3 different experiments of phosphorus treated alkane. And in the bottom graph, I'm showing you PE of the same samples. So overall, for all samples, we saw very little variation in pH. So pH actually just stays in the circumneutral zone that you see in here. But as expected, we saw a great decline in PE. So it was interesting to see that for reference samples, we don't have a clean curve like this one. It's much more short-term fluctuations in comparison to what you see in here. And reference samples, again, are the ones that did not receive sugar into it. And also an interesting conclusion was that we saw this two-stage decrease in P in both alkane and AMDR. And we speculated that this two-stage was when the prominent oxidant in the solution changed, or the electron acceptor changed, and the microorganisms was choosing the next one available. Okay, so when we analyzed the incubation solutions, we saw that the amount of soluble phosphorus and iron 2 was insignificant. And some of the potential causes for that are listed in this table here. So for example, some of the reasons for low iron 2 concentrations can be, for example, that iron 2 can also be found in solid forms. For low phosphorus concentrations, one of the reasons can be because of phosphorus reabsorption or precipitation, given the other elements that were also present in the solution. We saw the highest iron 2 concentrations and the highest phosphorus concentrations for phosphorus-treated metal shavings, but still the concentrations that we found were below the equilibrium concentrations for the phosphorus-treated materials, and it ranged between 0 to 0.25 milligrams per liter. And in the analysis of the incubated solutions, we did not find any potentially harmful trace metals. And this is how the phosphorus removal capacity of the PSMs before and after the anoxic conditions, the anoxic incubations look like. So each of the graphs represent one of the PSMs that we tested. And in the graphs, you see all the results for before, for the flow-throughs that were conducted before and after the incubations. We did not find any significant alteration on their behavior, on their phosphorus removal capacity. And overall, we can say that the effect of the anoxic conditions on iron-bound phosphorus and on phosphorus removal capacity was minor, which in practical terms means that, okay, we can use iron-rich PSMs in phosphorus removal structures with a bottom-up type of flow. Okay, so these are my three main topics for today, and now I have some takeaway messages. So the first question to answer, if phosphorus removal structures are a potential mitigation practice that is being considered, is are excess phosphorus levels a concern? And if they are, then we have two options, right? The first one being the prevention and containment of that source, which would be through conventional BMPs, or we also have the remediation option. So for remediation, we have long-term solutions, and I'm showing you here an example that can be phytoremediation, or we have short-term solutions, which is phosphorus removal structure. It is a short-term solution because it will start working immediately as soon as it is installed in the field. The choice of PSM, then if we decide that phosphorus removal structures are a good alternative for mitigating the phosphorus, the dissolved phosphorus in that condition, then we choose what is the PSM that we are going to use. So we have the option for a calcium-based PSM, and in this research, we investigated the use and behavior of steel slag. We saw that it can be used in both low residence time and high residence time. If a low residence time is expected for a phosphorus removal structure, then we recommend the use of 100% aluminum coated. If you're not very sure how well it will behave in a phosphorus removal structure, then a preliminary assessment can be made only based on the electrical conductivity, total calcium concentrations, and total iron concentrations. If a longer residence time is allowed for that phosphorus removal structure, then we can use an uncoated steel slag. And for making a preliminary assessment of how that will work, then we would analyze EC, porosity, and magnesium concentrations. If iron and aluminum-based PSMs are deemed more appropriate, given their variability or type of reaction, then we saw in this research that we can regenerate the materials once it is saturated with phosphorus. And for that, we can use two different types of regeneration. So we can use a regeneration with 20 pore volumes without recirculation, or 5 pore volumes with 6 recirculations. And then we also researched about the flow direction. So for those structures that are going to be built in flat landscapes with shallow ditches, we then saw that we can work with iron-rich PSMs in bottom upward flows. And for any other kinds of landscapes, we recommend the use of a top downward flow. It's easier to use, and it's what is the standard for phosphorus removal structures. So with that, with this research, we were able to advance our understanding on phosphorus sorption materials, and hopefully to increase the efficacy and the adoption of phosphorus removal structures. With that, I'll take any of your questions.
Well, thank you very much, Isis. And we can begin to take some questions. There's maybe one that's a couple showing up in the chat, but I'm going to go ahead and ask one myself real quick here. You included, when you're looking at the steel slag treatment materials, you're correlating, or different properties, chemical and physical properties you were looking at. And one of those that was related, you didn't talk about it, but it looked like it was electrical conductivity. Is that correct? So I wonder if you could comment on what was the relationship between, your observed electrical conductivity and what you think the impact of that was on your materials.
Yeah, I find electrical conductivity a very underused parameter, to be honest. Let me go back to that slide. Okay, yes. So the electrical conductivity, we measured that just putting a slag in a diluted, in the DI water solution. And the idea here, what we thought was that the electrical conductivity was actually being a proxy for the amount of calcium and magnesium that was available for reacting with phosphorus. So that is why we thought that it is a good parameter to explain the variability of steel slag to remove phosphorus.
Okay. Thank you. So we have a question here from Dr. Shir Mohammadi. He's saying, what is the chemical composition of a typical PSM? He said, you mentioned that the removal rate will depend upon both chemical and physical characteristics of the material. Can we grind up the materials to small pieces in order to increase surface area exposure?
Yeah, we can do that, but I wouldn't recommend it. Just because we found that finer particles, they actually, they are difficult to work with because they will interfere with the hydraulic conductivity of the structure, right? The hydraulic conductivity of the structure, as well as it can cause clogging. So of the pipes. Specifically for steel slag, what we saw is that when we use very small particles, we actually end up with a white cloud. It very rapidly, it is basically calcite, but it very rapidly it will clog your pipes. So it is not helpful for the longevity of the PSM.
Okay, here's another question. Said, how long do you estimate that an iron or aluminum-based system might last if you've got areas with high phosphorus levels in ditches or fields that are coming in maybe higher than 0.5 milligram per liter?
Okay. That's interesting. Actually, we have a software that was developed. It's called P-TRAP, T-R-A-P. It was developed by the USDA National Soil Erosion Research Laboratory. And you can actually put all your parameters, input parameters, to understand how long would those structures last, given your footprint, given your flow rate that you're expecting, given the concentrations of phosphorus that you're expecting in that structure. And so that's what I meant when I said these structures are extremely flexible. We can build them according to the necessity of the farmer or the environmentalist. For those two structures that I showed you, we designed them to last for 12 years. And by the end of those 12 years, we have the possibility of regenerate the material, right? So we had another 12 years that we could go on, and then we could regenerate again, but remember, with a decrease in efficacy after the second cycle of regeneration.
Since we're talking about regeneration here, one of the questions that occurred to me, so you've demonstrated that we can do this with like 5 pore volumes of water or solution,
yeah,
base solution. But that still sort of represents a lot of fluid. And so I'm wondering if you're sort of flushing, what does this look like in the field? I mean, it's one thing to sort of do it in a column in the lab, and how actually would that phosphorus sort of be recovered? Would you have to sort of flush it and then just capture all that solution and carry away this, these thousands of gallons of solution and find some way to dispose of that phosphorus that way?
Yeah. So the way that we would proceed to do that, and we took that into consideration when we were establishing the number of pore volumes that we would use. So 5 pore volumes for a normal sized structure, it can be carried in those tanks that carry herbicides. So the farmer could use those tanks for storing the potassium hydroxide solution. Then we would have a pump that would recirculate in the structure and back into the tank. And we would have another tank after the recirculations are done that would collect those the residual water. We would treat that with calcium chloride. So we would have the dissolved phosphorus on the bottom of it, precipitated, and then we can dispose the solution to the closest ditch, because it won't have a higher alkalinity, and the pH was okay. We tested that as well. It was also in circle neutral range, and that's it.
So you can actually precipitate the phosphorus into a solid phase, so you don't have this huge volume of material to deal with.
Exactly. Yeah.
Okay.
Yeah.
Are there any issues with anything else coming into the solution when you're fiddling with the pH or using very high pHs with potassium hydroxide? Did you notice anything else kind of coming into solution?
So there are
concern?
Not for the regeneration. We couldn't find any potentially harmful trace metals or anything like that. But for steel slag specifically, we have to think a little bit about the alkalinity of the steel slag. The pH is not a problem, just because it is quickly equilibrated once it reaches the nearest water body. But in terms of alkalinity, we don't like to use those steel slag that have a higher buffer capacity. So we look for the ones that have intermediate buffer capacity, just to make sure that it can keep those high pHs for calcium precipitation to occur, but it won't be a problem once the water is drained out to the ditch.
Okay. So Dr. Shirmahamani is asking again, can maybe this be done as simply as taking a bag full of slag materials and dumping them in a ditch and letting them just filter, or they need to be more highly engineered, as you've described?
Well, I mean, you could do that, but how long would that last? right? So one bag of slag, it will last for one flow event or so, right? So there are ditch structures. We can build these structures inside the ditch, so water flows through the PSMs. But we have to think about the total amount of phosphorus that can be removed by a certain quantity of the PSM.
If I may, Martin.
Yeah, sure.
Controlled drainage, water resides in the open ditch. So drain pipes, underground drain pipes drain into the ditch. I didn't mean just one bag. So if one could just basically fill in several synthetic bags, almost like, you put filter socks around the drain tiles, but in this case, drop in the ditch, under controlled drainage, especially really later portions of the drainage. Maybe at the beginning, there is a little bit sort of fast flow over the drainage structure, control structure, but it resides there for a while. So I was just thinking that if that simple type method could help a little bit to remove some of the soluble P.
Yes, I think so. And we have structures that are built that way, that are built directly in the ditch. But what I would say is that we look for hotspots of phosphorus, right, in the field. So once we are already in the ditch, we already have that phosphorus kind of diluted on all the water that is coming in. So once we treated it before, we have to treat a lower volume with a much more concentrated phosphorus concentration, right? So that is more adequate for phosphorus removal structures to work at their best.
Alrighty, well, it's 1 o'clock here. I think we'll bring this to a close, and we want to thank you once again, Isis, for